Hey everyone. So we are just getting our intro on here for AP Chemistry. We're just kind of doing our warm-up, getting your brains to remember stuff that we covered in regular chemistry. Okay, so this is just what I like to call Chapter 1 or Unit 1. Okay, and it's just our introduction. So let's talk about the most basic thing, the definition of chemistry. Okay, chemistry, what is it? It's the interaction of all things that we're made up of, okay? It's the materials of the universe and how they interact with one another. So it is the study of the materials in the universe and how they interact. Okay, so it's not just like chemical reactions, it's also kind of why your table is a solid, why water's a liquid, but it does involve chemical reactions like how the battery in your car works or the battery in your phone works, okay? Or why your drink bubbles up when you pour soda into a glass, okay? Things like that. Let's talk about those basic building blocks, which are atoms, right? Or we're just saying they are elements. It's that basic kind of Jimmy Neutron figure that you've seen where it's just a bunch of protons and neutrons in the center with these electrons zooming around the outside. Okay, so that's our atom. Examples of an atom are things like a carbon atom, which have the chemical symbol C on the periodic table, and things like a nitrogen atom, which have that symbol N. Okay, we also got other ones like iron, which have the chemical symbol of, if we remember correctly, Fe. And then we got gold, which has the chemical symbol of Au, right? Right, when you're in New York, the guy's trying to sell you gold change, he says, Au, want to buy a gold chain? But it's a great year, it's going to be a great year. All right, so let's talk about the next thing, when we combine those atoms, okay? When we combine those atoms, we could call them a molecule, okay? Molecule, two or more atoms. Okay, things like H2, that's a hydrogen molecule. You got H2O, that's a hydrogen molecule or compound. You got things like iron 2 sulfate, that's a compound, okay? When I say molecule, okay, everything could be a molecule. This is a molecule, this is a molecule, this is a molecule. But when I say something like compound, okay, compound is two different elements combined together. So this is a compound, this is a compound, but my H2, that's not a compound, okay? That's still a pure substance. It's two of the same elements, but it's still a molecule because it's more than one atom, okay? So all these are molecules, but only these two guys are compounds, okay? Because those are two different elements. Let's talk about pure substances, okay? Pure substances, we are just putting into two categories, okay? Pure substances are elements and compounds, okay? Yeah, compounds are technically mixtures of elements, but in the broad scheme of things, we're saying compounds are pure, okay? So if I have just iron, that's a pure substance. If I have a gold ring, that's a pure substance. Okay, if I just have pure water, not tap water, purified water, we're going to call that a pure substance as well. It's compound, okay? Things like CO2, that's also a pure substance. We'll also go with things like if I had pure sugar, okay? That is a pure substance as well. Let's talk about, so we got pure substances, that's one category, and it's just elements and compounds. right? But let's talk about the next thing, which is the opposite of pure substances, which is mixtures. Okay, mixtures. So now we're mixing things together. These are defined as a variable composition of mixtures, or composition of substances, I should say. Okay, now we're mixing things together. We're mixing compounds together, like your tap water. It's got water in there, but it's also got some iron, probably some calcium, maybe a little bit of lead, depending on where you are. Okay, and we define these mixtures into two subsections, which you might remember. Okay, mixtures. We got two types. We got homogeneous and heterogeneous. Okay, homogeneous, from its name, it's the same. Okay, it's a mixture that is the same throughout. There's not anywhere clumps, there's not any like separation. I'm thinking of things like Kool-Aid. It's the same throughout if you mix it up well. I'm thinking things like, let's go with soda. Okay, I'm going with things like steel. Same throughout. There's not any big chunks of stuff chilling in the way. What about heterogeneous? This is different throughout. Okay, so this is a mixture that's different throughout. The most basic I could think of is a pizza, right? It's not just all one same mixture. Okay, there's some pepperoni in the way, there's some cheese here and there. It's stuff that you could see, like Italian dressing. It'll separate out after a certain time. I think sour cream can also be a heterogeneous mixture. If it sits for a while, all that oil and liquid comes up to the top. Okay, so let's get a couple examples. Water, and I'm talking tap water here. Do we think that is homogeneous or heterogeneous? Homogeneous. It's the same throughout. There's no big chunks of anything. If there's big chunks in your tap water, I'd call a plumber. Okay, we got Kool-Aid. As I said before, what do we think that is? Homogeneous. Okay, it's the same throughout. No big chunks of anything. Let's go with dirt. Let's say you went outside and you picked up a big clump of dirt, which you guys probably do because you guys are animals, all right? Dirt, you pick it up just randomly out of the ground. Okay, I'm going to say that's heterogeneous. It's got rocks in there, maybe a bug or two. Okay, so that's heterogeneous. And then let's go with, let me think of a good one. Let's see. Taco. Okay, maybe that's not a good one, but that's what I thought of. So taco, it's a mixture throughout, right? It's not the same. You got meat, cheese, lettuce, sour cream. If you're cool, heterogeneous. It's not the same throughout. Okay? So that is kind of like the basic thing that we covered last year right at the beginning. The mixture of pure substances, which are your elements and your compounds, which is what we're dealing with mostly. And then you got your mixtures, which are homogeneous and heterogeneous. Next up, let's talk about chemical versus physical change, okay? Chemical versus physical change. Okay, so these are the two types of changes in chemistry, and I'm going to define chemical change first. So it's pretty much you're changing the molecular, you're breaking bonds and you're forming bonds. Okay, so I'm going to say one substance is changed into another substance. Okay, that's like photosynthesis, right? We're turning sunlight into CO2 and glucose, okay, and into oxygen. Okay, we're breaking the chemical makeup here. So say I got something like these are oxygens, and I'm going to say that these tiny black ones are hydrogen molecules. So we got a bunch of hydrogen and oxygen molecules floating around here, okay? and then all of a sudden they react together for some reason, and they make 4 water molecules, okay? That is a chemical change. Bonds were broken, and they were remade to form these new molecules over here. So that is a chemical change, okay? A physical change is, it's still the same thing. It's still the same chemical. It just kind of moves around a little bit. So I'm going to say for a physical change, the substance changes position. Okay, so substance changes position. So if I take water and I freeze it, it didn't become something else. It's still water. It just kind of got closer together. Okay, so let's look at ice. Really, if it's close together, it's really packed. So it's really cold. They're getting close to one another. Okay, their intermolecular forces are getting really strong. So this is just ice, right? They're all close together. They're still separated. Okay, these guys aren't touching one another. They're just close. It's cold. But if I heat them up a little bit and they turn to water, they're going to spread out. Okay, they're still the same though. The molecules haven't broken apart and formed something new. They have just separated a little bit. So this is a physical change. Still the same thing. They just spread apart a little bit so that they're not close to one another. That is a physical change. All right? So let's go over here and let's do a couple examples. Let's think about molding clay. Physical or chemical? Physical. I'm going to put a P there for physical. Right? It's still clay. You just change the shape of it. Okay? Let's go with burning wood. Is that wood anymore after you burn it? No, it's ashes, right? Also, a way to define physical is it's easily reversible, right? If I melt water, or melt ice, sorry, I could refreeze it. Okay, so it's easily reversible. If I mold clay, I could easily mold it back, so that's physical. So easily reversible is physical. Things that I can't reverse is chemical, okay? Cutting potatoes. When I cut the potatoes, do they magically turn into carrots? No, they're still potatoes. Okay, so that is physical. And let's go with rusting silver, which rusting silver is actually tarnishing silver. Silver doesn't rust, it tarnishes. Okay, but that's like turning silver into silver oxide, right? It's changing its composition. So that is a chemical change, right? Let's keep on going. Let's talk about just a couple more things. Let's talk about the scientific method, okay? We'll be doing that a lot in our labs. We'll be making sure that we are following the scientific method to the best of our abilities, okay? It's the way we discover new things. It's how new chemicals get developed. It's how new cures for diseases get developed, okay? So the scientific method is super important. It just sometimes gets abused or not done in the correct way. So the first thing we gotta do is we have to ask a question, okay? If I inject this person with a chemical, will they get cured of cancer? If I develop this new type of solar panel, will it increase the output of energy? Okay, that's how it all starts. And then what we might do first is some research. We might say, are similar solar panels done like this before? Has this chemical process shown any promise in any other types of people? Okay, we might do a little research and see if we're going to be performing an experiment or some sort, okay? Next thing we do is we make an educated guess, which is also called a hypothesis. Okay? We're saying think this chemical could cure cancer. I think it could not cure cancer. I think the solar panel could increase output by 20%, something like that. Okay, and then the next thing we do is we do an experiment. We try to make a non-biased experiment, an accurate experiment, an efficient experiment that helps us prove or disprove our hypothesis. And we're going to do that experiment in a non-biased way. We're going to make sure we're not just trying to prove our hypothesis just to become famous. We want to prove that the hypothesis is correct or incorrect, non-biased, okay? Next thing I gotta do after I do that experiment is I gotta analyze the data. We look at what the data is saying. Is it saying that cancer patients were recovering, that they were reducing their cancer cells, or were they increasing? Okay, was I getting more energy out from those solar panels, or was it worse? Okay, we gotta look at that data, and then we gotta compare to our hypothesis. So we pretty much form a conclusion, but we compare to our hypothesis. If my hypothesis was that this chemical is going to cure cancer, then I'm going to say, based on our conclusions, it actually was not successful or was successful. I think the solar panel will increase the output. Based on my results, yeah, I do think it'll increase the output. I do think we'll get more energy out of this type of science experiment. One thing that's super important, right? Other scientists have to prove your experiment or your hypothesis true as well. It can't just be you, okay? Other scientists have to do it. Unfortunately, a lot of scientists don't like doing that. They like working on their own stuff. So that's a big problem that we have in science, is that there's not a lot of scientists out there that are willing to give it a shot and try to test your hypothesis. So that's where we get some like biased results, like with anti-vaccine, okay? One guy just said it, didn't really look at his results too much, just said, yep, vaccines cause autism and other diseases. And then we have this whole problem now where we have this misinformation campaign that's gone out of control. So make sure that if you become scientists someday that you are not being biased and that you're having other people prove your experiment or your hypothesis, okay, in an unbiased way. All right, let's just talk about one more thing. Let's talk about scientific law and scientific theory, and then we'll be done. For this intro session, okay? So we got scientific law, and we got scientific theory, okay? Scientific law kind of sounds like, like how it sounds, right? It's what will happen. It tells you what will happen. Okay? Like I could say, hey, it's the law of gravity. I know when I drop this marker, it's going to fall. That is a law. Okay? That is something that we have proved time and time again, and that is going to happen. Okay? It's going to drop into my hand. Scientific theory, okay, it explains why something may happen. Okay, a classic example of this is Einstein's theory of relativity. Okay, he's saying that if you go near the speed of light, time should slow down for you. Okay, we don't have any real way of proving that. If we were going to go at the speed of light, we need tons and tons of energy, our mass would decrease, and actually if we were going the speed of light, we wouldn't experience time at all. So it's just a theory. We think that's what's going to happen, but we have no real way of proving it. We just don't have the tools, the resources, or the science behind it to prove it. Okay, so theories are things that we think may happen. Scientific law is that we know for sure this will happen. I drop this marker, it's going to fall. Okay, and one last thing, let's do accuracy versus precision, and that'll be that for this intro video. All right, so accuracy versus precision. The best way to do this is just to explain it through a picture. Okay, so we got a target here. Okay, accuracy is, yeah, you're kind of close to the center. You're pretty accurate. Okay, you were accurate, but were you precise? Okay, were those dots close together? Okay, were you in the same spot every single time? Here I'd say no, you're accurate, you're close to the center, but you are not precise. They're kind of spread out, your shots on this target. Okay, let's do another target. I know my targets are real consistent. And say you shot and you were boom, 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 boom. That, I would say, is precise. But are you accurate? No, you're far off the center. Okay, last but not least, okay, last target. Say we got all dots in the center. This is accurate and precise. Okay, why is this important in science? This is important with our science experiments, okay? Most of the time, you're going to be in this accurate, not precise range. You'll get data points in the accuracy range, but you'll be up and down a little bit. You'll have like a time where you were dead on, you didn't have any errors. One time you might have added too much of a chemical, another time you might have added too little of a chemical. So it's good to be aware of if we're accurate and we're not so precise. This is a dangerous one, okay? Precise and not accurate, okay? This is where in a lab we are getting data points all in the same spot. So we could be saying like, oh man, we're getting all this data, it's all in the same spot, I must be correct. But what if you were making the same mistake for each of these data points? Say you were adding too much of a chemical each time. So you might think that you're accurate, but really you're not. You're just really precise, okay? So it's good that we kind of keep that an open mind to our results and we're not saying, okay, they're close, that means I'm correct. No, we could have just been making the same mistake the whole time. And here, when we get data points close together, let's make sure that we're doing things correctly, that we're kind of comparing with other people's results and seeing if we are accurate and precise at the same time. Okay, that's our intro just on the basics of chemistry. I hope you enjoyed. Next up, sig figs.